All right, now accepting answers. First of all, what would the correct notation for this be? D theta dt. What'd you get? That's it?
Yeah.
Anybody get an answer? Cole.
D theta dt equals 1 over radical 1 minus y over 10.
What?
Well, it's going to be a number, right?
Oh, the answer? Yeah, radical 10 over 10.
Kylie.
I did not get that. I got a very small decimal. It was negative 0.0216.
Negative.
0.0216.
Anyone else get that? Other answers? First of all, should the rate at which theta is changing with respect to time be negative or positive? Why? The angle formed by the ladder and the ground is decreasing. Do you agree? So the rate that theta is changing should be negative. So that's just a quick little checkpoint as you're kind of going through it. All right. Did you use SOHCAHTOA? How many of you used sine? Cosine? Tangent? The guy who stayed on the beach for too long. He was a tangent. That was bonus content, by the way. All right. We decided this was 8 yesterday, didn't we? And again, this is only at the snapshot in time. He's taking a picture as the guy's falling down the ladder because it's entertaining. I didn't tell you guys my ladder story, did I? This is a real life situation. You want to hear about it? Yeah. It was 3 years ago. It was a cold, wintry day. We actually had a snow day. It was a cold day. It was too cold to go to school. And so, did I tell you about the workshop that I have? I have math stories related to this workshop. No? Yes? It's a detached 2-car garage, okay? That I have all my tools in. Like my woodworking tools that I build stuff with. I was building the shop, okay? It took me a while because I was doing it by myself. Because I'm lonely. All right. So, day off school, I'm like, this is awesome. It's really cold out. I'm still going to go out and work, okay? So, the trusses were up. Like, actually, the roof was on too. Like, here's the roof. Here's the side view. Here's the bottom. Your trusses go like this. And they've got, some webbing that goes through them, all that kind of stuff. As they kind of go, whatever. I was putting in an access door up high here. So I could put, once my ceiling's in, I could still get access to the attic of it, right? So my head, where am I? Oh yeah, my head is up here. And it's getting weird. Okay. My ladder was going like this, up into the trusses. So I'm working on the top edge of this window, all right? I'm wearing 4 layers of Carhartt, it was super cold. And to do this this door access, whatever it is, I had to put my ladder inside and then outside sometimes. Well, there was snow on the ground. So the snow stuck to the bottom of my ladder. And it got turned icy. I go to the inside, I set it up, climb up the ladder, I'm working up there. All of a sudden, or first of all, flashback a little bit. My son Micah, who was 8 at the time, he never ever does this, but for some reason on this day, he was going outside to play, and he's like, "Hey Dad, what are you gonna be doing?" I'm like, "I'll be working up on the ladder in the shop for a little bit." He's like, "Well, I'm gonna hang around. I'm gonna play around here just to make sure you're okay." He never he just always goes and plays wherever he wants to play. All right, so he's outside playing whatever, and my ladder, this bottom was covered in ice. And by the way, there is like a pile of lumber, like construction lumber down here. And I made tall ceilings in the shop just so I could, have long boards and that kind of stuff without hitting ceilings. So they're like 10-foot ceilings, all right? And so I'm up with this ladder, icy bottom, the ladder, like quicker than I could even realize, just boom, all right? But not fast enough that I couldn't calculate the angle at which no. So instantly, my first reaction was just grab on whatever I could. So I grabbed the trusses, and I'm hanging there, and I had zero flexibility. I'm like wearing so many layers, face is covered, hat, everything, gloves. And I'm like, Micah! So he comes running inside, and he's like, what can I do? I'm like, he's not strong enough to lift this ladder and put it up properly. And I didn't want to jump down because of the pile of lumber. I would have like broken my leg or something. My wife was downstairs in our basement on the opposite side of the house in our office. So he goes running downstairs, goes and gets her. It felt like 4 minutes later. I'm just hanging here. And I'm like, I can't hang on much longer. And so like the garage door track goes this way. The garage door's here. And so like I swing my legs up and over the garage door track to like get some sort of relief. She came in time. She's like, what do I do? Should I set up the ladder? Like, what should I do? Yeah, just set up the ladder. So she sets up the ladder and I climb down safely. It was scary.
That's crazy, right?
Yeah. Anyway, real life story. Real life story. So if you would have taken a picture of me as the ladder was falling, okay? The top of the ladder was 6 feet up. The bottom of the ladder is 8 feet out. All right, I know this is not to scale. But the angle we're trying to find, well, the rate at which the angle we're trying to find is that angle right there. Here are your choices. I want to help you guys narrow it down because when you have a choice, yesterday we didn't have a choice. Pythagorean theorem, only option, right? Today, with that angle, you have a choice between sine, cosine, and tangent, and there are some options that are better than others, okay? Option 1. By the way, we called this X, we called this Y, we called this L yesterday. Option 1, sine of theta is Y over L. Do you agree? Why couldn't I put 6 over 10? Because it's changing. If you put 6 over 10, that's a geometry problem. You're only finding the angle at that instant. You can't find a rate of change because you haven't allowed for any calculus, right? You haven't allowed for any derivative. Do you agree with that? Okay. I have to call it Y over L. Option 2, cosine of theta is X over L. And option 3, tangent theta equals Y over X. Does anyone have an idea which one the best option or options would be? Sine or cosine? I agree. Why? What's that? L is always 10, and so whenever you take the derivative, dl dt will be 0, because the length of the ladder is not changing, and that will simplify your derivative quite a bit. Does that make any sense? Because the tangent one, you're going to have, now you have to use the quotient rule. You have to use the quotient rule, but you're eventually going to get a dy dt and a dx dt, and it's just going to add more complexity to the problem. So I would say it will work, but it will be difficult. And another reason why it will be difficult is because the derivative of tangent of theta is secant squared theta times d theta dt. Secant squared is kind of complicated to evaluate. Versus the derivative of these are just a sine or a cosine off by a negative. Should we do sine? Should we do sine? All right. What's the derivative of sine of theta with respect to t? Cosine theta times d theta dt. Quotient rule, low, d high, dy dt, minus high, and d low is going to be 0. You can write dl dt, but dl dt is 0 over log. All right, now that we have taken the derivative, I cannot emphasize this enough. Now that we have taken the derivative, we have allowed the picture to be in motion. There's a dx dt. Nope, there's a dy dt. There's a d theta dt. Things are allowed to move. Okay? Now you can plug in constants. Now you can plug in constants because things are in motion. Cosine of theta. Ooh, what's the cosine of theta at that instant? 8/10. Very good. Ready? Cosine of theta is adjacent over hypotenuse. Cosine of theta is 8/10 at the time in question. So in for cosine of theta, I'm going to sub in 8/10. All right, what's L at the time in question? 10. What's dy dt? -2. Very good. Over 100. 10 squared. So I have d theta dt is -20 over 100 times 10/8. I'm going to multiply both sides by the reciprocal, 10/8. All right. What do you get? -1/4. -1/4 units. Radians per. I think it was seconds, wasn't it? Was it minutes? Seconds? Radians per second. This class will always be in radians. Physics? Degrees. That's kind of cool, right? What's a radian, by the way?
The length or the circumference, the radius surround.
How many radians does it take to get around a circle?
2
Right, 6.28-ish. It takes, so if you were to stretch a string around in a circle, it would take 6.28 radians to get around the circle, right? You agree? So when you think this through, like how fast is that going? Well, run 1 radian, 2 radians, 3. Okay, I can kind of, it's kind of tough to picture for that. I think degrees per second would probably be easier to visualize, to be honest. But that's just the unit of measure we use for calc. Does that process make sense? Okay. What about if we did cosine? Derivative of cosine, negative sine of theta times d theta dt. We'd have a low d high minus a high. Okay, we'd need dx dt. Here's another thing. When you start doing the problem, do you know dx dt? Isn't that something we had to find from part A, if we want to call it that? How fast is the bottom moving away from the wall? There's another red flag. If I use that, I have to trust that I got that right from letter A. Does it make sense? So this might make more sense to do in this problem to do sine of theta. Cool. I actually think we're going to skip this problem for now. It's a long problem. I will give you the gist of it just so you have more experience with a triangle. But I think we're going to be better served doing a new type of problem that is challenging for students. All right. I'm going to read it, but we're not going to solve this. Don't write it down. I just want to walk you through it. All right. A police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner, is now moving straight east. when the cruiser is 0.8 miles north of the intersection and the car is 0.6 miles to the east, it is determined with radar. It is determined with radar that the distance between them and the car is increasing at 15 miles per hour. So if I called this Z, dZdt is increasing positive at 15 miles per hour. If the cruiser is moving at 60 miles per hour, isn't this the cruiser? If the cruiser is moving at 60 miles per hour, don't I want to call that negative 60? I know it seems weird, but do you agree? The Y component is decreasing. The cruiser is getting closer to the intersection. Do you understand what I'm talking about here? All right. What should I call that? Negative 60 miles per hour. dy dt. I have dz dt. If the cruiser is moving at 60 miles per hour, what is the speed of the car? I'm trying to find dx dt. What do I need? Well, is this a Pythagorean theorem problem or is this a SOHCAHTOA problem? Pythagorean theorem, x squared plus y squared equals z squared, 2x dx dt plus 2y dy dt equals 2z dz dt. I have an x, I don't have a dx dt, that's what I'm trying to find. I have a y, I have a dy dt. I don't know z or dz. Well, I do know dz dt. I need to find z, right? 0.6, 0.8. Remember the 6, 8, 10 triangle we talked about yesterday? So 0.6, 0.8, 1 mile. You could do the Pythagorean theorem to solve it, but that's the gist of that problem. Another one just like the ladder problem, all right? Just a different application. Now, another type. So we've done a ladder problem. We did the angle with the ladder problem. We did a sphere problem with the balloon. The third type I want to show you is it's called a conical tank. Water runs into a conical tank. Please write this down. You're going to want to have this one down. This one tends to be confusing for students. Water runs into a conical tank at a rate of 9 cubic feet per minute. Positive or negative? Is it filling up or empty? Filling up. So positive, 9. Again, let the units talk to you. Cubic feet per minute. Cubic feet per minute. What should we label that? dV dt. Very good. dV dt is 9. And I thought most of you are realizing at this point, it's like, hey, I'm the volume of a what? I'm the volume of a cone, conical tank. I should probably write down the volume formula for a cone. Everything all right? You need to pass or anything? So what is the volume of a conical tank, and what does this look like? Well, the tank stands point down. So it's got some sort of, have you ever seen cones like this that have some sort of support structure around them, like a ring? Ooh, kind of like when you're, look at an ice cream place when they have cones. Like, you know how you like stick a bunch of ice cream cones in like the support structures, circles, like rings? Kind of like that. Only this might be like a agricultural application. The tank stands point down and has a height of 10 feet. Is that a changing height or is that a constant height? Constant. That's the height of the tank. So here is the H that we're talking about. It's the height of the tank, and it's 10 feet. We're going to make a couple adjustments here as we keep reading. And a base radius of 5 feet. Okay, base radius does not mean the bottom of the picture. The base radius is the circle part on the cone, right? So the base radius is 5 feet. Everybody good with that? The base radius of the cone. How fast is the water level rising when the water is 6 feet deep? Do you understand the problem? Like, do you understand that a constant volume of 9 cubic feet per minute being filled in, the water level will rise quickly at first, and then the water level will slow down. The rate at which the water level is rising will slow down as the radius of the tank increases. Do you agree? Okay, so that's why this is a calculus problem, right? If this were a cylindrical tank, not too bad. Conical tank, a little different. Now, we have some different things here. If I call this H, I need to be careful. This is the height of the water is 6 feet deep. So I'm going to put height of the water is 6. All right. Let's see if we have everything we need or if we need to change or adapt or find some missing information. I think we can all agree we need the volume of a cone. Do you agree? Anybody know the volume of a cone?
Pi cubed times h over 3. I looked it up.
You said, hold on. You said pi r cubed?
Yeah.
Times a third h?
Times h over 3. Yeah.
That's it. That's if the conical tank has the same base radius as it does height. I would agree with that. A general cone is just 1/3 pi r squared h. So if h and r are the same,
Then there's an extra h in that one. There's an extra variable.
oh, you're right. I forgot I even wrote that h. Yeah, I think that's supposed to be squared. Double check.
Yep, squared.
All right. What's the problem that we're going to deal with this equation? Anybody anticipate an issue? What do you think, Cole?
We don't have the radius is changing.
Yeah, we're looking. Do we have the HDT? We're trying to find what? How fast is the water level? We're trying to find the HDT. Do you agree? So we're going to need what? We're going to need a dVdt. We're going to need a drdt. And we're going to try to find the HDT. You see the problem? What else is the problem when we got to take the derivative of that equation? What is the overarching derivative rule of this volume formula? Product rule, very good. Product rule. So we're also going to need the, and by the way, are these R's and H's talking about the tank R and H or the water R and H? The water radius and height, correct? Because when you do the drdt or the dhdt, it's how fast the water level is rising or how fast the water's radius is increasing. Bless you. Not the tank isn't changing, so that's not that one, right? Would it be helpful if we could write r as a function of h or h as a function of r, so we only have one unknown on the right-hand side? Would that be helpful? Would we rather have h's in our problem or r's in our problem? H's because we're trying to find dh dt, right? So can I write r as a function of h? Can I write r as a function of h? R equals something h. Is there a relationship between the radius of the water and the height of the water at any given time? Do they have a constant or predictable relationship that we could model with an equation? When the water level is 6 feet, the radius of the water will be 3. When the water level is 8 feet, the radius of the water will be 4. Where did you get that from? Yeah, the tank has a ratio of 5 to 10 radius to height. Doesn't that mean the water's going to have the same ratio the whole time through? 1 to 2? Now, for this problem, right? What if the tank changes shape in the next problem? There's a different ratio. Maybe it's 1 to 3, maybe it's 2 to 5. Do you agree with that? Okay. And where does that come from mathematically? Well, if you were to drop down a height, did they call this a right conical tank? Okay. Sometimes they will say it's a right conical tank, meaning it's not oblique. This is an oblique conical tank. Okay? Just when I thought I was getting away from the glitches of that. Maybe it's just me. All right. This is an oblique conical tank. A right conical tank means the vertex is at a right angle to its height. That's a bad way to describe it. The circular base is perpendicular to the height of the tank. All right? So because of that, do you see the similar triangles formed? We have a similarity in these triangles. Because the triangles are similar, the sides are proportional, more than you really want to know. So we have the radius of the water, and we have the height of the water. And now you could set up a proportion, right? 5 over 10 equals r over w. Oh, 1/2, right? 1/2 r equals 1/2 h. That was the very nerdy way to explain it. If you just want to look at it and say, oh, 5 is half of 10. The radius is half of the height. Done. Right? What if it's 2 to 5? The radius is 2/5 the height. Pretty easy, right? Now, why is that important? Well, wherever I see an r, I can plug in 1/2 h. You with me? And that's going to save us from a product rule. It's going to save us some time later. What's a half squared? A fourth times a third. A 12th. Pi h cubed. This is the specific volume formula for this problem because of the ratio between radius and height. What do we want to take the derivative with respect to? Time. So dv dt is, ready? 3/12, 1/4, pi h squared times dh dt. Let's fill in what we know. Let's solve for what we don't. What was dv dt in the problem? 9. Careful, what's h? 6, right? It's the height of the water, not the height of the tank. All right, we have 36 over 4, which is 9. We have 9 pi. So we're going to divide by 9 pi, and we get 1 over pi. One over pi. So close to a third. Close to a third of a, what's h measured in? Foot per, is it minutes? I think so.
Yes.
Thank you. 1 over pi feet per minute. All the time? Is that the rate the height of the water is changing all the time? No, only at that snapshot in time. Only the picture when the water level is 6 feet. And the radius of the water was 3 feet. Does that make sense? That's kind of a tough problem because what students will do, they'll get into the volume formula, and look how messy this gets. Ready? First times the derivative of the second. Ready? First, 1/3 pi r squared times dHdt plus the second, h, times the derivative of the first, 2/3 pi r dr dt. Then they're going to try to find a dr dt. You with me? See where it gets kind of messy. Now, what if you forget and you get into that trap and you do that on a quiz? Can I find dr dt? dr dt equals 1/2 dH dt. Uh-oh. I need to know dH dt, don't I? That's what I was trying to find in the first place, wasn't it? Okay. But what you could do is when you get to that dr dt in the problem, you'll put in 1/2 dH dt, and then you'll be able to solve for that dH dt generically. Like you'll have two parts because of the product rule. You have to combine the dH dt's, probably factor out and solve. Does that make any sense? Don't do that. All right, do it this way. You guys don't find this as exciting as I do? Is that just a general rule of thumb for calculus so far this year? This is some cool stuff. Whenever a farmer is just not cultivating, harvesting their crops, and you see corn just flowing into the silos, like whoever's driving, wait a minute, I just need a moment. Some calculus right there. I'm gonna go dive in it. Hi, Wendy.
Is there always going to be like a ratio that you can use like a variable to?
Yeah, because these are always going to be similar triangles. Because this is a shared, do you see how this big triangle has this angle down here? And this little triangle has this angle down here? They share that angle, and they share a right angle because it's a right conical tank. So those triangles are always going to be similar by AA. So real quick, what if the radius of the tank was 7 and the height of the tank was 13? Then R equals 7/13 H would be your ratio. Right? You plug in 7/13 H in for R. Any other questions? Good question. Related rates. Balloons, so spheres, cones, triangles that have to do with sides, triangles that have to do with angles. Okay, those are the main types you're going to see. I think these are fun. You like them? Real. Can I tell you a nerdy story that I thought of? When my dog was just a puppy, we used to live at this like farmhouse, and there was a telephone pole in the yard because they had to put power back to the barn. And so we put my dog on a leash, and the leash was tied around the telephone pole in the yard. Okay? So she was just a puppy. She didn't know any better. So she'd get herself wrapped around the pole with her leash, right? And I'd be up in the kitchen on the second floor, like watching her, wishing I didn't have to go down and like every 5 minutes unwrap her from the. So I'd watch her, and guess what she did? She figured it out. She would unwrap herself. Guess what I thought? As her radius of her leash is increasing, I wonder how fast the area that she can roam, that area of a circle, is increasing. Did I take a picture? And at that snapshot in time, I calculated. No, I never. Related rates are all around you. Okay? If you're nerdy enough to see your own related rates out in the real world, please share it with the class. Yeah.
I didn't get a paper.
Oh, that's unfortunate. I thought I gave them 4. Did this have an 4?
Jackson probably took another one to practice.
Want to?
No, I'm good.
Thank you.
Yep. So number one, you're doing an airplane prop. We never went over the homework, did we? We can do that. All right. Number 1 is another airplane problem. Number 3, you got a conical cup. 5 is a balloon problem. You got air escaping. Air escaping. 9 is a man that's 6 feet tall walking. Now, this one's a little different. I want you guys to challenge yourselves. Don't just turn into turtles and give up on it. 20. There's a back. Yep, and then they saw all the answers there. All right. 20. You got a boat being pulled into a dock by a rope. I don't know if you guys understand the picture here. A boat is being pulled into a dock by a rope attached to it and passing through a pulley on the dock positioned 5 meters higher than the boat. Oh, and it should be than the boat. THAN. I didn't type this up. My grammar is much better than that. Do you understand the picture? Here you go. Boat. Ooh, that's a deep boat. It's going to be pretty unstable. I apologize. Pretty buoyant. Did I tell you guys about my boat story? Did I tell you about my raft?
No.
Do you even know me? My friend and I built a raft when we were in college and floated down a river for 3 days.
3 days straight.
Yeah,
Just living
How
in
far
the
did you
boat.
get?
lived on it.
How far did you get?
Oh, I don't know, 20 some miles. I don't know. We didn't float all day. We got stuck for one day. Stuck for about 4 hours. The tree falling across the river. Couldn't get over it. I mean, our raft was like 300 pounds. It's loaded down with food and supplies and tent, like our own little homemade tent, water,
What river were you?
the mighty Tuscarora. Yeah. I have pictures if you want to see it. We took 4 55-gallon drums and then tied like lashing straps around them, like ratchet straps. Built a framework around them, put a top. We had under compartment storage for a cooler, for clothes, for supplies. We had a hatchet in there. We had all sorts of stuff. We had a dry compartment for it. We had a reel on the back to put like a tarp up and over us for night. We had lounge chairs to sleep on.
How many of you were there?
Just 2.
2, including you.
My friend and I, yeah.
Where's the rest?
I got disassembled. This was like 17 years ago. 18 years ago. All right, a boat is being pulled into a dock by a rope, passing through a pulley on the dock positioned 5 meters higher than the boat. Is that 5 meters changing or constant? Very good. If the rope is being pulled in at a rate of 2 meters per second, the rope is being pulled in at a rate of 2 meters per second, whether you call that L or Z, dz dt is going to be -2, right? How fast is the boat approaching the dock? That means horizontal. When it is 12 meters away from the dock. Got it? We had tiki torches on all 4 corners to light us up through the night. Did you do it again? Oh yeah, yeah. Is that for like a project or something? Just for fun. What's that?
I feel like you just have way too much free.
Well, see, college life, I had I waited tables at Red Robin, and I made such good money on Friday and Saturday nights. I didn't work the rest of the week.
Okay. So you were just like, let's build a raft
Yeah.
and float down a river?
So my friend and I both waited tables, and we're like, hey, let's go. So first we floated down in tubes, and we had a blast. We're like, hey, we should build like a raft and float down for a couple days.
See, like, me and my friends have those kinds of things.